Joey is going to talk to us about compiling to linear neurons.
All right, can you hear me fine? Is the mic on? Yeah, cool. So yeah, I'm Joey. I'm a PhD student in the PL group at the University of Pennsylvania. And this is a joint work with my advisor, Steve Zdancewic, Konrad Kording, and also in collaboration with Nedda Amin, who's at Harvard. So the question we're interested in this work is, how do you take a differentiable programming language and extend it with first-class discrete structure? So this means that something as simple as like a conditional, you can use it wherever you want in the language, and things don't break. So for instance, in these languages, they're very popular in machine learning for implementing things like neural networks. But when you're implementing neural networks, you can't just throw a conditional wherever you want, because you can easily break the derivatives that these networks need in order for learning to work. But these are issues that compilers can ultimately correct, and this talk is essentially about how you do that. Now, to begin, I want to introduce a simple problem that'll help kind of illustrate what kinds of programs you can and can't write in these differentiable programming languages. So the problem is just about conditionally transforming an input image. Now, if the input image is a 1, don't do anything, just apply identity. But if it's something other than a 1, you should try to transform it into a 1. Now, what's nice about this task is that it has both discrete and differentiable structure. So the discrete structure is just the conditional, and the differentiable structure is transforming that image into a 1. So that's not something you just sit down and try to write. That's typically something that you try to throw a bunch of data at a neural network to learn. So a typical approach in differentiable programming languages is what we're going to call the indirect approach. And we call it an indirect approach because you're not trying to directly specify the conditional structure of the task. Instead, what you're going to do is you're going to try to set up like the skeleton or an architecture to solve the problem. And this kind of pseudocode that I have here is just kind of prototypical of the kinds of code that you would write in a differentiable programming language. And again, what you're trying to do is just set up like the skeleton of a network. And the important kind of mental model that should be in your head, especially if you haven't used a differentiable programming language before, is that you're just defining some kind of function over a vector. And what you're ultimately going to try to do is instead defer to learning to figure out what exactly these W's should look like, which are matrices. Now, this is essentially the main approach that people use in machine learning, which has been overwhelmingly successful for all kinds of things, right? Like language modeling, image recognition. And this is the main way that you program in languages like PyTorch and JAX. But one key issue with this style of programming is that it crucially depends on getting the architecture or the skeleton of the network correctly. So you can easily set up an architecture or a skeleton that doesn't help you learn some task. And so in practice, you actually have to experiment a lot to get things to work, especially if you're in a domain that hasn't been studied extensively. So we're interested in how to constrain that search so that maybe you can use a compiler to help find what the right architecture could look like. I should also say that sometimes this process of like experimenting to find an architecture is called in like a tongue-in-cheek way graduate student descent, because you basically just throw 1,000 grad students at a problem, and then you slowly start to figure out like, oh, this kind of circuit motif is useful for the task. So our work is trying to explore a more direct style of programming, where in the cases that you have discrete structure in the task, you can actually just try to specify it. So in this approach, you could write a program that looks something like this, where you're writing a program that decomposes the task into first detecting if the image is a 1, and then if it's a 1, you apply identity, and otherwise apply a transformation to turn the image into a 1. And so hiding in this program is still some element of the indirect approach. You have to specify the network or the architecture for learning what a 1 is, or for transforming an image into a 1. But you're decoupling now the conditional structure of the task into simpler parts. So it's way easier to design a network to detect if an input image is a 1 than it is to do the entire task altogether. But for this to work, you need to somehow be able to compile that program above into the network below. And in order to explore the design of these compilers, we introduced a minimal calculus that we just call Cajal. So Cajal is a small language. It's basically just Booleans and higher order functions. But for now, it's more than enough to basically deal with the conditional image transformation problem. At the end of the talk, I'll mention how you can go far beyond just these simple data types. So I just want to briefly talk about what a linear neuron is. And they're effectively just linear maps. So the exact definition of what a linear map is not super important for this talk. But it looks something like this. And the important thing to note, though, is that a linear map could be represented as a matrix, and that this matrix is actually specifying the coefficients of some linear neural network. Now, there's a world where we could have just called the paper compiling to linear maps, but we chose to emphasize the linear neurons perspective because they're a much more specific kind of mathematical object. So there are tons of linear maps that you can't implement in JAX or PyTorch, or that look anything like a neural network. So drawing on some very nice insights from the semantics of linear logic, we decided to give a linear type system to Cajal. And it turns out that if you give a system linear types, you're giving it some chance to be, for the programs to compile to linear maps. There's a long understood connection between linear types and linear algebra that we're exploiting in this work. So with nonlinear typing, the issue is that you can freely duplicate assumptions in your typing judgments. And in short, what this will mean behind the scenes is that when you're trying to define a semantics for your language and compile them to linear maps, often the fact that, for example, in this program, you're duplicating the assumption that x is a Boolean causes issues in your proofs. And so these like structural properties of the type system have a deep, deep implication on your ability to do this kind of a trick. So with linear typing, again, you're not able to do this. It's a lot more restrictive on how you can duplicate assumptions in a context, for example. And so behind the scenes in Cajal, linear typing is doing a lot to make sure that we can take a program like the one above and compile it into something like below. And so now I want to talk a bit about how exactly the compiling would work for a conditional, but I want to start with an example that doesn't work, but it's almost there. So what we're doing here is compiling a not operator. If you instantiate x with true and evaluate it, it should give you false. Instantiate it with false, evaluate it, it should give you true. And the way that the rules work, or the ways to understand the rule, is just the compiler, which I'm denoting with denotation brackets, is taking a typing judgment and returning a function of some vector, sigma. Exactly how the variable rule works is not deeply important, but what you should understand is that the compiler is taking a judgment and spitting out some function between vectors. For constants like false and true, it returns a constant function. In the case of false, it always returns vector 0, 1. In the case of true, always 1, 0. In the paper, we talked a lot about what goes wrong if you try to make different choices at this stage. But again, for the conditional example, it's not super important to understand. Now, for compiling conditionals in this way, which we call like a kind of hard branching conditional, what you're doing is you're just checking if the first component of the vector of the compiled condition is 1. So I should also say that this rule is kind of emblematic of what would happen if you tried to naively implement a conditional in something like JAX or PyTorch, and exactly why you don't see conditionals so often in the middle of like a training loop in a neural network. So this rule has actually some very nice properties. If you, for example, passed in the denotation of true, you would get back the denotation of false. If you pass in the denotation of false, you get back the denotation of true. So it's mirroring the behavior of the source program in some nice way. But the problem is that despite the function even being differentiable almost everywhere in sigma, the derivative is just completely uninformative. So the derivative is measuring how a change in, for example, alpha 1 and alpha 2, or in sigma, corresponds to some change in the actual output of the rule. And the actual output of the rule is only ever going to be 1, 0 or 0, 1. It doesn't depend in any non-trivial way on alpha 1 or alpha 2. And what that means as a consequence in a neural network is that if you put this in the middle of a network, the way that the learning algorithm works, it would basically block the flow of derivatives to any part of the network that precedes it. So it would essentially break your ability to learn. The remedy we take in our work is to consider something like soft branching. So with soft branching, what's effectively happening is that you're sort of compiling each branch of the conditional, running both, and then combining them and scaling them according to the compiled condition. So we compile assumptions in the exact same way. And like before, if the input is sigma, or the input to sigma is the denotation of true, you get false, vice versa. So it also mirrors the behavior of the source program in a nice way. But unlike before, you can actually get informative derivatives from this kind of an equation. So for example, you can get non-zero derivatives. And if you place something like this in the middle of a network, you wouldn't block gradients in the same way that the previous rule would. So we use a rule like this to compile a program like that above into a network that looks like that below in Cajal. So I won't go through the rest of the compiling rules here, since it's not necessary for the motivating example. But in the paper, we talk a lot about the interesting things that pop up when you try to compile lambdas and applications. And those formal specifications are ultimately checked by a correctness theorem. So it might be helpful to just think of the correctness theorem as equivalent to the soundness and adequacy of a denotational semantics. But more intuitively, what we're asking of the correctness theorem is just, can we predict what the compiled code is going to do? So in this case, can we predict, if we know how a program evaluates and what it doesn't evaluate to, can we predict what the compiled code is also going to evaluate to, or what it's equal to, or what it's not equal to? And if we can do those things, we call the compiler correct. Now, the appendix contains detailed proofs of all these things, but I do want to highlight one lemma that is I got wrong quite a few times in trying to state correctly, and that's doing a lot of heavy lifting in the paper. So this lemma on the bottom right basically just says that the compiler is taking programs, typing judgments, and mapping them to linear maps. And it does a lot of heavy lifting in the proofs, but also it's the lemma that kind of justifies this story I've been alluding to informally about the connection between Cajal, linear types, and linear algebra. It's also the lemma that essentially justifies the title of the paper. So in one sense, our compiler is correct, but a stronger test of correctness would be if it actually helps us solve this conditional image transformation problem, which interestingly goes beyond the notion of correctness I just told you. So to test this, what we did is we implemented Cajal. It's just a simple 200-line prototype implementation that extends PyTorch with conditionals, where in the back end, it's basically translating those conditionals into the soft branching equation that I showed you. And so we trained basically both of these networks to solve the task. And we were interested in the final outcome of learning, so did it help? But also just qualitatively, how do networks learn in super weird different ways when you use these compiled networks? So the next couple slides are just going to be zooming in on two examples comparing both models on how they, across training time, how they learn the task. But afterwards, I'll talk about a more generic measure of their performance across the entire test set. I'll begin with the direct approach. So remember, the task is to apply identity if the image is a 1, and otherwise to try to transform that image into a 1. And from left to right, I'm showing them intermediate model outputs across training time. So each training step just means I updated the parameters of the network, which means I've just slightly changed the function that it's computing. So in about the first 100 steps, what the direct approach is learning is to do identity for everything. So when the input is a 1, that's good, that's correctly solving the task. But when the input image is a 4, that's definitely very wrong. And in the next 100 steps, what the network learns to do is just try to stop overusing the identity for everything, especially for when the input image is a 4. And for the remainder of training, the network is just kind of like refining the answer, which mostly just means it's trying to get a better and better reconstruction of the identity for when the input image is a 1. And the last images I have on the right are essentially the solutions that the network converges to after 3,000 training steps. And in summary, it sort of ends up doing the right thing. It learns the identity reconstruction on the 1, and it transforms the 4 into something that looks like a 1. Now, for the indirect approach, the learning dynamics are a bit simpler. In the first stage, it's basically just learning a constant 1 function to apply to everything. And there's a bit of noise in it. So then in stage 2, it tries to figure out how to sort of refine that answer by just removing small amounts of pixel noise in the image. And generally, what it learns to do is just apply a constant function to everything. The key distinction, though, in these models' behavior is just that the indirect approach is struggling to recover the identity for when the input image is a 1, which, to me, I found very interesting, because this is like a stupidly simple task. So I thought, OK, this could learn it, right? But at the same time, your takeaway shouldn't be like the indirect approach could never solve this task, right? It just might mean that you need to throw graduate student descent at the problem a little longer to find the right architecture for solving it. But again, the point is to see if when there is discrete structure, can we not just specify it directly to avoid that kind of search? So beyond those two training examples, we computed what was called PSNR, peak signal to noise ratio, on each of the models' behavior across training time. PSNR, in short, is just measuring how good of an identity reconstruction is the network computing across training time, because that was the measure that most distinguished true model performance. In short, if PSNR is high, that's good. If it's around 20, it means that the network just learned to produce a constant 1. The data in blue are from the direct model, and the data in red are from the indirect approach. And the TLDR here is just that these data are consistent with what we just observed in the previous slide. So it's not that we sort of got lucky on a specific configuration of training, but we've trained everything across 5 different seeds, different learning rates, different batch sizes, and beyond some degenerate cases where no model learns anything in the bottom row, the trends from the previous slide still hold. So the paper contains 4 additional experiments on different kinds of programs that you can write in Cajal. And again, the data are, in short, consistent with the story I showed in the conditional image transformation task. And these experiments were encouraging. So since POPL, we've gone quite a bit beyond just Booleans and started considering more interesting data. So for example, if you change the target to instead think about linear recurrent neural networks, so these are neural networks that have feedback connections, you can introduce data like natural numbers. And so what this allows you to do is introduce first-class kind of primitive recursion over the natural numbers in a differentiable programming language. Going even beyond that, you can introduce more intricate kinds of recurrence in neural networks to even account for algebraic data like trees and a list data type and stuff like that. And I'm happy to talk more in the question period about additional extensions that I think are well posed, but that I just haven't had the chance to get as far to in my notes. So I want to end on a kind of more speculative note just about the current state of differentiable programming. And this is a quote from Alan Perlis in a speech he gave in 1981, essentially about how much it sucked to program in machine code in the 50s. And basically what he's saying is just that you couldn't just take an algorithm in your head and put it in a machine. It required a ton of experimentation to get right, if you could get it right at all. And in those frustrations, he just started to think about maybe developing a high-level programming language and working on compilers. And the 50s were a very long time ago for me, so I don't know exactly what he means by programming experimentation. But absolutely, in some sense, when you program in a differentiable programming language, there is this degree of very annoying programming experimentation you have to deal with. So I think maybe we should be thinking about how to build higher-level languages for JAX and PyTorch, and maybe that means that they'll include first-class discrete structure of the kind that I'm trying to study in Cajal. With that, I thank you all for your time, and I'm happy to take questions.
Right, thank you for the talk. I was hoping that you could explain to me something about linearity in a few slides back, to the example where you define the direct approach, basically.
Sorry, which example?
The one where you say if one of image, then something image.
Oh, yeah, at the beginning. Something like that.
This one's fine. Right,
Yeah.
so what I was wondering is where does linearity come in here? Because image is being used
Yes,
in the scrutiny and then in the branches as well. So that was my question.
Yeah, so this is a great question. So we made an important, this was not our first choice in modeling decision, but what we're doing with Cajal is we're only modeling a linear subfragment of some bigger language. This wasn't the first thing we did, actually. And originally, we had some more complicated linear, nonlinear calculus where you could literally type a program like that. That turned out to be a mistake because I did a ton of proof work and found that at the end of the day, when it came to actually implementing the extension to PyTorch, the only part that was interesting was the linear subfragment. So that's not to say that there are no interesting questions in studying the extended language, but at least with respect to this task on solving the conditional image transform, all the interesting stuff is happening in the linear subfragment. And that was a hard-earned insight. I literally threw away many months of my life in prepping the actual work because I realized it just wasn't that insightful for the question.
So how come, sorry. So how come can you have image show up both in the branches and in the scrutiny of the if?
So the way that this is modeled literally in Cajal is as an open, it's an open judgment. So it's a free variable. So you can imagine replace one of image with the free variable that is just whatever type you want, essentially. Mm. And then behind the scenes, this needs to be coerced into some vector space. It could be R10 or something. But
Got a question right here.
Hi. Okay, so the notion of a derivative also seems to correspond really well to like the sensitivity of a function. And sensitivity type systems also are linear type systems, and I'm wondering if you had considered using a sensitivity type system here in this setting?
Yeah, I know. I'm like I'm aware of like fuzz and I haven't thought as much about where you get the most traction, where you could get traction out of using something like fuzz's type system. It's an interesting point. Mostly the reason why I haven't thought about it is I feel like there's like 3 other type extensions that are like immediately tractable and offer cool stuff to do, but I would be happy to talk more and like brainstorm about.
I should have prefaced also with delightful talk. Thank you.
I wanted to ask more about the evaluation or your approach for evaluation.
The experiments?
Yep. Does it make sense, since you're trying to impose or make neural networks compliant with some specifications, does it make sense to use neural networks verifiers as part of your way to measure the success?
For example, like what kind of notion of success are you interested maybe in?
Like, could you ask for every image that is classified as 1, the output would be the identity, for example?
Yeah, so this kind of gets at that gap, at the gap between the theorem I proved, and then there's this experiment I need to do to show that it's like ultimately correct, right? And you're saying there's maybe some interesting way to add some machine learning to complement this. I think that sounds fine, like well posed to me. Yeah.
Okay, thank you.
The next speaker could set up as well, please. Last question.
I have a question about your example.
Yeah.
So the 2, 1, can that be a constant function? What's actually being learned? What does it mean to convert something to a 1?
Sorry, say that first part.
You either return the image, or you convert it to a 1. What does it mean to convert something to a 1? Can that be a constant function?
Yeah.
What does it have to be?
Originally, when I was thinking up of the task, I thought that the network would learn like this cool, slightly different 1 for every image. But ultimately, it ends up just learning a constant 1. So if you look at like the actual behavior beyond just those 2 examples, what will happen is that for 1s, it'll do identity for everything that's a 1. And then for like a 4, a 3, a 2, whatever, it'll learn a constant 1. But I think that's more of a symptom of like the training data than anything deeply relevant to the core stuff in the talk. But
I would have expected the constant, to be honest.
Yeah.
Okay. Well, thank you very much, James.